Let us consider the XOR problem. We have dealt with this when we discussed multilayer perceptron, then we looked into it when we discussed the radial basis function network and then how we could solve the XOR problem. Now we will study this from the perspective of support vector machines or SVMs. And this was done by Cherkasy in 1998. So we start with a kernel and we assume this kernel to be a polynomial type given by k of x comma xi is 1 plus x transpose xi, and I assume that these vectors are in a 2-dimensional space. So x is x1 x2 transposed and xi is having 2 coordinates xi1 and xi2, and this xi is this xi1 xi2 transposed. Now I can compute this kernel x comma xi. So what I have to do is 1 plus x1 x2 multiplied by xi1 xi2, and this happens to be a scalar, and then I raise it to the power 2. So if I expand this out, I have 1 plus x1 xi1 plus x2 xi2. So I have 3 terms and I square this up. So this is straightforward. So I can compute this as 1 plus x1 square xi1 square plus 2x1 x2 xi1 xi2 plus x2 square xi2 square plus 2 x1 xi1 plus 2 x2 xi2, right. I have totally 6 terms. I mean, you do expansion a plus b plus c whole square, I get a square plus b square plus c square plus 2ab plus 2bc plus 2ca. Now just as the way I did earlier, I treat this kernel as an inner product of 2 vectors, and that is what I need to do. So let us express this kernel as an inner product of phi of x and phi of xi. So I can compute phi of x as this vector 1 x1 square root 2 x1 x2, then x2 square, then root 2 x1, then root 2 x2. I have 6 terms and I have 6 coordinates here. Just observe what I am doing here and things become pretty straightforward. Similarly, phi of xi can be written as 1. I pull this out, I am just grouping all the red terms. And this 1 is basically one dot 1, right. So, phi of xi is 1 xi1 square root 2 xi1 xi2 xi2 square root 2 x i1 and then root 2 x i2. So, I can put a transpose here to make sure everything is right. Now, phi of x times phi of xi, or the inner product between phi of x and phi of xi, can give me k, right. Phi of x transpose times phi of xi gives me this kernel. So, for the XOR problem, so I have data points -1, -1 that corresponds to a response -1, -1 comma +1 that corresponds to a response +1, +1 comma -1 that corresponds to a response +1, and then +1 comma +1 that corresponds to a response -1. I can formulate the Gram matrix K where each element of this matrix is the kernel that acts on the vectors xi and xj given by kxi comma xj equals phi transpose xi times phi of xj. Now, each xi xj can take these pairs -1 -1 -1 +1 +1 -1 +1 and +1. Okay. So, I get a 4 by 4 matrix when I compute the Gram matrix. You can verify this computation, and I get this matrix as 9 1 1 1 1 9 9 9 that 1 9 1 1 that is I have the element 9 along the diagonal and every other element is a 1. Okay. This is sort of a straightforward computation because I have to evaluate phi of xi and phi of xj over these points. For every possible pair of points I have 4 points. So, I get a 4 by 4 matrix, and this is what I have over the points for the XOR problem. Now, from the dual problem, we can set up the objective as follows. The objective Q as a function of the Lagrange multipliers is computed straightforwardly as follows. It is alpha 1 plus alpha 2 plus alpha 3 plus alpha 4. Just recall that it is sigma I equals 1 to 4 alpha I minus summation minus half times summation I equals 1 to 4 summation j equals 1 to 4 your alpha i's alpha j's di dj and then the kernel acting on this, right. If I simplify this, I get this as follows. Is going to be alpha 1 plus alpha 2 plus alpha 3 plus alpha 4 minus 1/2 this quantity here. So, I have a lot of terms. I think I need to get this brace really quite big. So, now this q of alpha is a function of the Lagrange multipliers, and this is from summation okay. This half sticks out here, and the terms inside are basically from this double summation. Now, once we are set with this dual problem, the rest is sort of straightforward. We do a Debye q upon Debye alpha I for each of these alpha i's from I equals 1 to 4 and set that equal to 0. So, doing this yields 4 different equations. So, we have 9 alpha 1 minus alpha 2 minus alpha 3 plus alpha 4 equal to 1. So, look into this cost here. Just take the partial derivative with respect to alpha 1, you get one equation, another derivative with respect to alpha 2, alpha 3 and alpha 4. So, you do this, you get these set of equations. So, I have pre-computed them. So, it is straightforward for me to write this a priori, and you can verify this calculus straightforwardly. So, I have these 4 equations. So, solving this set of equations, solving the set of equations, I get alpha optimum for each I to be 1 upon 8 for I equals 1 to 4. Now, all 4 inputs xi's from 1 to 4 are support vectors, and you can verify this. And q of alpha, when I plug in this, I get 1/4, and in the second part in the cost is 0. So, half of norm of W naught square happens to be 1/4. This implies norm of the optimum weight vector is 1 upon root 2, and with this I can plug in the optimum to solve for the optimum value of W naught to be I equals 1 to 4 alpha optimum I di phi of xi. So, I take for all these points I equals 1 to 4, I plug in to this expression. So, I get 1 upon 8 minus phi of x1. So, I have the corresponding pairs di, right. I know for a pair xi di I know what the values are, and I have computed alpha optimum I to be 1 upon 8, which I pull out. So, I get 1 upon 8 times 4 terms minus phi of x1 plus phi of x2 plus phi of x3 minus phi of x4 and if I solve for this, I get the optimum weight vector to be 0 0 minus 1 upon root 2. You can verify this to be this quantity. Now, from the optimum weight vector I can compute the optimum hyperplane, and this is given by the equation W transpose phi of x is 0. So, W optimum transposed phi of x equals 0. So, I plug this in, I have 0 0 minus 1 upon root 2 0 0 0 times 1 x1 square root 2 x1 x2 x2 square root 2 x1 root 2 x2, this is equal to 0. So, just a third term remains. So, this implies x1 x2 equal to 0 is the decision boundary. Right. So, I would want to keep this sign a negative sign. So, I just formulate y is minus x1 x2, and let us see how this solves this problem. So, I have the points minus 1 minus 1 minus 1 plus 1 plus 1 minus 1 and plus 1 plus 1. So, for this, so these are my x's in R2 and these are my responses y computed from minus x1 x2. For minus 1 I get a minus 1, for a plus 1 I get a minus 1, for the other two terms I get a plus 1. This is as desired from my very first step, right. So, I started off with the XOR response in this manner. So, therefore, this equation y equals minus x1 x2 is what I consider to be the equation for the discriminant boundary for the XOR problem. But I think there is a take home message here, right. If you observe this function or this response y which is minus x1 x2, this is nonlinear. Right. I take x1, I take x2, and then I multiply by minus 1 and I get y. This is how I can realize. But I was able to solve for this y completely using a linear optimization framework, and this is essentially a linear framework. Because I am talking about a hyperplane which is W naught transpose phi of x, and that is my linear equation. But when I evaluate the linear equation, what I get is basically in this form, which is y equals to minus x1 x2, and that is sort of my response, right. So, I think with this example we can construct SVMs to solve our classification problems. This is a very important illustration. So, what you will have to do is start with the data points and the required response, and given this data set, that is the set of points and the desired response, I formulate my kernel. And you may ask this question, how should I choose this kernel? This is again subjective. There are various kernels, various inner product kernels, and the choice of the right kernel depends upon my applications. Typically we invoke these polynomial kernels, and depending upon the power p, I can lift my input vector to an arbitrary higher dimension that I can get, that I want, right. So, in this case I lifted a 2-dimensional vector to a 6-dimensional vector, and I was able to solve this problem in a 6-dimensional space. That means I was able to get a linear classifier in a 6-dimensional space, which I would not get in a 2-dimensional space, right. So, the choice of the dimension is again critical, and that needs to be experimented, but there is a link to the VC dimension, to how much we can lift, right. So, once I am in the feature space in a higher dimensional space, then I formulate my Gram matrix for all the pairs of data points, and I get the objective function. I can use the primal problem, or I can also formulate using the dual problem. So, dual happened to be easier in this case because it involved just the Lagrange multipliers and directly dependent on the data points invoking this kernel. So, I chose this framework. So, now you can compute the you formulate the dual problem, solve the optimization problem in the dual space, get the optimum Lagrange multipliers, and then you can plug that into your equation for the weight vector, which is optimum, the optimum weight vector based upon the conditions that you get by setting the derivative of the Lagrangian with respect to the weight to be 0, right. You get that condition. So, solve for that W, and then everything is sort of straightforward, right. Then you have the cost, then evaluate the cost, and then you compute W transpose phi of x, and that settles this problem. Okay, this is very important. So, so we have realized how we can solve this problem, but one small detail, the phi of xi over each of the data points is fused into the solution for W naught, and that is an important detail. And when we take phi of x is a general form of this vector form that we have as a result of a component from the kernel. Okay. So, this completes the details of this design, and I hope you can use this formulation in any of the practical problems. So, this is a toy example. In real life cases you may not find something as straightforward as this. So, you may have with noise, you may have to bring in some constraints in terms of your loss functions, etc. So, there in those problems, if you set the problem carefully and you set up the constraints and the optimization framework, you can do the math simplifications and feed this to any solver using a package, and hopefully that will give you the right results. But a very important thing that you have to understand is to get a feel and sense of the geometry of the problem and what we are actually doing in terms of concepts, and that is the central idea towards discussion of this example. Okay.